While I've been looking at solutions to non-homogeneous second-order equations, I want to actually define what I have been finding. The particular solution, which we denote as y sub p, is essentially what I've been finding. A particular solution is just a solution that satisfies the non-homogeneous equation. On the other hand, we can also find what's known as the complementary solution. The complementary solution is denoted by y of c, and it's a solution that satisfies the corresponding homogeneous equation. So we keep all of our coefficients the same, but set f of t equal to 0 and solve that. And finally, we have the idea of a general solution. So the general solution is the particular solution plus the complementary solution. So let's look at some examples of this. Here I have the differential equation y double prime plus y prime equal to 5. Our previous video said that since 5 is just a constant, we need to let y be equal to a. This means y prime would be 0 and y double prime would be 0. However, when we stick that into our equation, we would have y double prime plus y prime equal to 5, which is not true. So we do have an issue. And this is why it's important to talk about the complementary solution. And so let's start by finding that. The complementary solution. For that, we needed to solve our equation, r squared plus r equal to 0 in this case. We can factor that into r times r plus 1 equal to 0. So we have that r is equal to 0 and negative 1. So that tells me that my complementary solution is equal to c1 e to the 0t plus c2 e to the minus 1t, or c1 plus c2 e to the minus t. On the other hand, the particular solution, we want this to be of the form a, but that's going to cause an issue because now this term and this term are not linearly independent, and we need them to be. So before, when I had a repeated root, I also had issues with independence, and my result was to multiply one of them by t, and that's what I'm going to do here. I'm going to make my particular solution at. Then y prime would be a, and y double prime would be 0. My differential equation originally said y double prime plus y prime is equal to 5. So now I have that a is equal to 5. Now this gives me my particular solution is 5t. So my general solution would be the complementary c1 plus c2 e to the minus t plus 5t, and that would make sure all of these terms are linearly independent. Let's look at another one. This time y double prime minus 6y prime plus 9y equal to e to the 3t. For my complementary solution, I need to start by solving my quadratic. This would be r squared minus 6r plus 9. And for complementary solutions, we let these be equal to 0. This can be factored into r minus 3 squared, which tells me that my roots are just 3 and 3. Therefore, my complementary solution would be equal to c1 e to the 3t plus c2 t e to the 3t. When I find my particular solution, it would normally be of the form a e to the 3t. However, then we'll notice that this term here and this term here are not linearly independent. So we might want to include a t term. However, then we have issues with this one here. So we're actually going to include a t squared this time. That way it will be linearly independent from both of these. And then I'm going to go ahead and rewrite this as at squared e to the 3t. Taking my first derivative, I have the derivative of the first times the second plus the first times derivative of the second. For my second derivative, we'll do the derivative of the first times the second plus the first times derivative of the second gives me 6 at e to the 3t plus derivative of the first times the second plus the first times derivative of the second would then give me a 9 at squared e to the 3t. Using my original differential equation, we have y double prime, so 2a e to the 3t. I'm going to go ahead and combine these two here to get a 12at e to the 3t plus 9at squared e to the 3t. I then need to do minus 6 times y prime. So 6 times 2 is 12, so that's minus 12a t e to the 3t. And minus 6 times 3 is minus 18 at squared e to the 3t. Plus 9y, so that would be 9 at squared e to the 3t. And this should be equal to just e to the 3t. Looking at our coefficients, we'll start with the coefficients of t squared. So here's a 9 at squared minus 18 at squared plus 9 at squared. So that would give me a 9a minus 18a plus 9a. And then on the right, there's no t squared term, so equal to 0. So that did not give us any additional information. Next, we'll look at terms involving a t. Here's a 12 and a minus 12. So that gave me 12a minus 12a. There's no t terms on the right-hand side, so this should be equal to 0. Once again, we get 0 equal to 0. Finally, if I look at my constant terms, terms without a t, I have a 2a on the left and a 1 on the right. So we get a is equal to 1/2. This tells me my particular solution is 1/2 t squared e to the 3t. My general solution was my complementary solution, c1 e to the 3t plus c2 t e to the 3t, plus my particular, 1/2 t squared e to the 3t. Let's scroll down a little bit. Let's suppose we also have some initial conditions for this. We know y of 0 is equal to 1, and y prime of 0 is equal to 2. Let's start by figuring out what the derivative of this is. The derivative of the first term would be 3c1 e to the 3t. The second one, I would have the derivative of the first times the second, plus the first times the derivative of the second. And then my last term, I have the derivative of the first times the second, plus the first times derivative of the second. So that would be 3/2 t squared e to the 3t. Y of 0 is equal to 1, so I know y of g, if I stick in 0, I get 1 back out. So that would be c1 times 1 plus 0 plus 0. So I have my value for c1. If I go ahead and come down here, my general solution, I know what c1 needs to be. We also know that y prime of 0 is equal to 2, so that would be a 3c1 plus c2 plus 0 plus 0 plus 0. We know c1 is 1. So that gives us that c2 is equal to -1. So we would have minus t e to the 3t plus 1/2 t squared e to the 3t. My next one, this time I'm not going to solve for my constants, but I do just want to get the general idea of the solution. I'm going to start with my complementary solution. r squared plus 2r plus 2 equal to 0. You can try to factor this, but you won't be able to. Quadratic formula gives us negative 2 plus or minus the square root of 4 minus 8 all over 2. This is going to simplify to negative 1 plus or minus I. So we have alpha is minus 1 and beta is 1. This tells me my complementary solution. C1 e to the minus t cosine t plus C2 e to the minus t sine t. Typically when I wrote this, I wrote e to the minus t times C1 cosine plus C2 sine. So I went ahead and just distributed that out. When I find my particular solution, the e to the minus t means I need an e to the minus t piece over here. And sine tells me I need a times cosine t plus b times sine t. However, we also now see that this term here and this one here are not linearly independent, so we're going to include a t. And this piece here and this piece here are also not linearly independent, so we're going to include another t. We can then rewrite this as t e to the minus t a cosine t plus b sine t. And like I said, I'm not going to solve for the constants, but we can now get yg by adding these two things up to get our general solution.